Welcome back. This is the final video for Unit 1. This is going to cover sections 7 and 8. So we're talking very briefly about the scientific method. And this is something that is definitely a review topic. You've had it as a freshman in biology, in 8th grade, maybe whatever class you took. So you should have some knowledge of the scientific method. So I'm going to give a very basic overview and then we will keep moving along. The scientific method is a systematic approach to solve a problem or answer a question. So we are trying to solve a problem or we are trying to answer a question. Systematic approach just means that we are using a system. We're using the same steps every time for consistency, and that way we know what's going on. The scientific method has some steps, and it all depends on what textbook you're reading as to what the exact steps are. But just to boil it down, first thing, you need to make observations. And the reason that I say you have to make observations first, if you are trying to solve a problem, you have to observe that there is a problem. If you want to answer a question, you have to observe that there is a question to answer. That's why I put make observations first. The second idea is to formulate a hypothesis. A hypothesis is something that we'll get into in a minute, but it is just an idea. It's an idea that we are going to be testing. And the third, perform experiments. Other versions of the scientific method will include things like they may consider data collection a step. Conclusion may be a step. Revisions may be a step. But those all vary. These are the three things that I see consistently regardless of the textbook. Some definitions. A hypothesis is an idea that can be tested. It's a potential answer to a question. So I made observations and I asked a question. My hypothesis that I form is a potential answer to the question. It doesn't mean that I'm right. It just means that I have an idea and I want to know, is this idea right or is this idea wrong? A couple of ways this could go in science. A lot of times the way it goes in high school is we're trying to prove ourselves right. On the other hand, in the real scientific community, usually what they do is they ask a question, they formulate a hypothesis, and then they do their best to prove it wrong. It makes it a lot more rigorous. It's a lot easier to prove yourself wrong than it is to prove yourself right. Using the scientific method, we will test a hypothesis by conducting experiments. So our hypothesis may or may not be supported. If your hypothesis is not supported by the experiment, it could be revised, meaning I am going to change my hypothesis. I have been proven wrong, and now I have a second idea. And rather than giving up, I'm going to test my new idea. A hypothesis that is supported needs to be tested again. Within the scientific community, if you told them that I saw this problem, I made a question, I made a hypothesis, and my experiment proved me right. And they're going to say experiment. And the idea is if you only ran your experiment once and it worked, it needs to be tested again. If you go to somewhere like Purdue or another school where it's very science heavy, you're not going to run an experiment once. You're going to run it 3 times, 5 times, 10 times. If you were a grad student, you'd probably run the experiment 10,000 times. It needs to be tested again. Next thing is a scientific theory. And a lot of times the word theory is used incorrectly. Usually people are using the word theory when they mean hypothesis. So they might say, I have a theory that, well, actually what they have is a hypothesis. I have a hypothesis that this is the case. A scientific theory is a hypothesis that is supported by many experiments. Another important piece is that it attempts to explain the phenomena. So not only does my hypothesis work in experiments, I'm trying to provide an explanation as to what's going on, why this is happening. Another term that's commonly confused with theory is a scientific law. A scientific law is also supported by experiments. So we have these two things in common. They are both supported by experiments. But a law does not attempt to provide an explanation. It works. It works every time, no matter what. It's a law. But I don't know how to explain it. A couple of examples here with some big physics names. So some examples. The law of gravity. You've heard of it. It's from Sir Isaac Newton. The law of gravity is supported by a lot of experiments. You can run an impromptu experiment with the law of gravity. I don't know if you can hear this or not, but I'm about to run an impromptu experiment with the law of gravity. Did you hear that? It worked. I dropped a dry erase marker and gravity pulled it down towards the floor, towards the earth, and that was gravity working. Does anybody know how to explain gravity? No, actually we don't. We have physicists out there who have spent their entire lives studying how gravity works. We've made great scientific progress in the last 30 years, but we still don't have this nice, neat little idea of this is how gravity works. It just works. Here's an example of a theory, the theory of relativity. Albert Einstein. The theory of relativity actually is somewhat complicated, but there are experiments that support it. For instance, one part of the theory of relativity is called time dilation. And what happens is it is thought that time moves slower as an object is moving faster. Now, it's not noticeable for us because when we're standing still 0 miles per hour, when we're driving down the highway 55 miles per hour, if you're flying in a jet, maybe 400 miles an hour. It's not enough of a difference in speeds to make a difference. But what they've done is they take small atoms that are unstable and they can put one on the shelf and they're going to put one into what's called a particle accelerator. So one of them is sitting still on the shelf. The other one, which is exactly like it, is going to be sent around this track and they're going to get it up to speeds close to the speed of light. At least you're going to try. And so then when they stop and they look at the two of them, which should be exactly the same if they were treated the same, and then we end up seeing that the one that was moving faster is not the same age as the one that was sitting still. So it's supported by experiments, and Einstein is trying to explain some things. It's a little bit complex beyond even the high school physics course that we have here. But that would be the difference between a theory and a law. One last piece, we have something called a model. A model is a tool that scientists use to explain something. It could be a lot of different things. But it is a representation of a scientific principle. As far as our classroom goes, sometimes it's plastic models. They look like molecules or atoms. Sometimes it's a drawing. Sometimes it's an equation, like a chemical equation. Sometimes it's a written explanation. It could be a table, like the periodic table. It could be a computer model. It could be etc. We're not really limited, but a model is just a tool that we use to represent a scientific principle.